waves with the same frequency, wavelength, and amplitude travel in opposite directions and interfere. Okay. A variety of scanning waves can occur when a string is fixed at both ends. We talked about that last chapter, actually. All right. Now this is going to be, you cannot not pay attention. Not now, okay? This is one of those things where you have to focus.
Second semester. Paying attention.
That's our second strike.
3 strikes.
No, you found my job too.
Oh, your name?
He has at least one. I remember.
That's one. Next time is for Daniel Lynn in physics.
Under merit.
Okay, so vibrations of a string of a musical instrument usually consist of standing waves. Okay, standing waves again are same frequency, same wavelength, same amplitude, traveling in different directions, and they interfere. Okay, now it says the greatest possible wavelength of a string is this. I'm going to show you why. This is. Imagine this is a string that's being plucked on a guitar. Okay? What is the definition of a wavelength?
This is distance from like point to point.
Like drop.
Really, yes. I use trough to trough or peak to peak to describe the wavelength, but really it's
One cycle.
one cycle. The length of one cycle.
Like if I say like a fixed point.
Sure. Yeah. So, for example, if I go like this, from here to here would be a wavelength.
Yeah.
But if I kept going, I could say from here to right there would be a wavelength. They're the same distance. Does that make sense? Okay. Now, if you look at this standing wave, first off, quick reminder, nodes are when you're at a point of
Equilibrium.
equilibrium or no displacement, correct?
Oh yeah, because node.
Okay, so here's a node, here's a node, correct? And antinodes are a place of max displacement, okay? So if you look at this, assuming this is a string, and this is where it's fixed on one side of a guitar, and here's where it's fixed on another side of a guitar, what you have is half a wavelength.
Oh yes.
This would be a full wavelength,
Oh, it's like we did.
right?
Around the 3 states.
Does that make sense? Okay? So, what this is saying, okay, the greatest possible wavelength of a string is going to be, of length L would be 2 times L. Okay, this would be our biggest wavelength we could have on this particular string. Even though it's half, so, right, wavelength. Okay, we said that this is half a wavelength, correct? So what would the actual wavelength be? 2L. Does that make sense? Okay, let me explain this again. This is the length of the string right there. Okay, that's the length of the string. We said in this particular case, we have half a wavelength. So a full wavelength would be twice the length of the string.
Yes.
2L. This is the greatest possible wavelength you can have. Could you have smaller wavelengths?
Yeah.
Yes, but you cannot get any greater than that. Yes. Remember, wavelength is how basically, for example, if I were to compare a big wavelength with a small wavelength, does that make sense? This is the biggest possible wavelength we could get. Okay, now let me show you, pull up in your books, I'm going to show you a couple other examples of this. So I don't know what page, it's in section 3, it's the page after the introductory. Okay, it's 419, top. It is?
Yeah.
Oh.
The first harmonics.
Oh, cool. Okay, so I want to connect what the largest wavelength is going to be. Okay, so we said this is the largest possible wavelength. What does a large possible wavelength tell you about frequency?
Frequency is less
Low.
than low.
It would be the lowest frequency, right? If you have your highest possible wavelength, that would correlate to your lowest frequency. This is what we would call our fundamental frequency. Our lowest frequency is going to be our fundamental frequency for standing waves and sound of instruments. Okay? Now, we can have multiples of our fundamental frequency, and that's what we're going to get into harmonics. There's the first harmonic, which is your fundamental frequency. The second harmonic would be a multiple of your fundamental frequency. Your third, your fourth, and so forth. Yes?
So it's like on a string of a guitar, the string you plug that, like that's the lowest note you can play on the string unless you like move the bridge or whatever.
No, you can have multiple standing waves on a. I'm just giving you
No,
to have the longest wavelength.
I mean the greatest length of the wave. So you'd have to move one of the notes for then it to be a different wavelength.
Yes, but you can have more than two nodes on. And, that's what this next visual is going to help try to explain. Okay, so I guess it's in your notes. I wish I had it. Yeah, oh, sweet. Okay, so now notice how the string length is exactly the same. Does everybody see it? Okay, from here to here to here to here. Okay, so what you now have in this situation, you've got 3 nodes and 2 antinodes, and then in this particular case, your wavelength is 1L. Because from here to here is a complete what? Wavelength. The other one's 2L is because half of the wavelength is L. So the full wavelength would be 2 times the length.
Does the wavelength always go up and then down? Like, can it go down?
And that's just the wave pattern. I'm not sure what you're saying.
Start.
So is the most common?
Oh, never mind. You get the same.
Is the most common frequency second harmonic? Since that's just a regular.
I don't know what would be the most common. All I know is that all of the harmonics are going to be multiples of your fundamental frequency. Okay? So then here would be another example. Okay, I have 3 what we would call standing waves. Okay, this would be 1 wavelength from there to there, correct? That's 2/3 of the length. Are you seeing it?
Yep.
Okay, another way you could do this is you could take the fundamental frequency and multiply it by 3. Same thing.
Oh, it's here.
Why 3?
Because it has, this is 1 frequency, this is going to be, you have 3, this is half of, does that make sense? You've got 3 standing waves, you have 1 standing wave.
3 halves.
No.
No. If you're talking wavelength, you would use this. But if you know the fundamental frequency, you're going to see how this is going to make the math easier. If we just know that every harmonic is a integral multiple of your fundamental frequency. Okay? And here, we should have 2 full wavelengths. There's 1, there's 2.
So why is it 1/2 of this?
Because I have 2 wavelengths in the string length. So 1 wavelength would be half the length of the string. Right? 1 wavelength is half the string. Right? This is saying the wavelength of the fourth harmonic is half the length of, when you have the 4th harmonic, you have half the length of the string. Okay? Now, we're going to continue to progress, and I'm hoping I can watch a little video here that does a pretty good job of kind of talking about how this works in instruments, because it becomes even more difficult when we have to apply it to instruments. Okay? What you're going to find is you can take a particular fundamental frequency, and if you are in the 2nd, 3rd, 4th, 5th harmonic, all you really need to do is take that integral multiple of your fundamental frequency. And that's what this equation is showing. Now, I want to go back. I said this is your fundamental frequency, right? That represents your fundamental frequency, because this is when your wavelength is the longest and your frequency is the Smallest, correct? Okay, we had an equation that looked like this. What was it? It's different in the physics book as it is.
V equals F.
Is it F?
Yeah.
That was, okay. Because it's different in different books. So it's that? That's what your physics book is?
Yes.
Okay, so this is the speed of sound. This is your wavelength. This is your frequency. Okay?
I do not remember.
This is from last chapter.
Yes.
Yeah, but I don't remember.
No, I just speed of sound.
I think I changed it to C because that's what it was in advanced chemistry book, or at least I mentioned it.
I know you mentioned that in class, but I don't.
Okay. Anyways, I'm not too worried about that. So what you have is if I can replace the wavelength with 2L here, divide by 2L, that's what you have.
Where's the other?
V divided by 2L. The N is just saying that's the whole number integral that you can multiply by the fundamental frequency to get the second, the third, the fourth, the fifth harmonic. Does that make sense? This is an easier way of doing, instead of taking and doing this. This would be much more difficult. This is a lot easier. Okay? A lot easier mathematically.
So we can only use that equation for first harmonic,
No.
but it's set up for first harmonic with the 2L and the
Yes.
like 1.
If your first harmonic, N is 1. If you're in your second harmonic, N is 2. If you're in your third harmonic, N is 3. So if N is 1, you're solving for your fundamental frequency.
Oh, I was looking at this on the first page. That's just the first.
Oh, okay, yeah. So this is specifically when you've got a vibrating string, okay? When you have a vibrating string, you should have nodes on both ends, correct? That gives you the full harmonic scale, okay? And I know that I'm not going to get too into why you have the full harmonic scale versus when you don't. I want to get to a YouTube video. I'm hoping we can get to it. Okay? When you have a string and you've got nodes on both ends, okay? The harmonic series is exactly the same of an air column when you have it open on both ends. That would mean antinodes on both ends. So if you either have antinodes on both ends or nodes on both ends, they're harmonic series that are going to be exactly the same. And I want to get to a YouTube video that will kind of explain what this looks like. Okay, notice, this is exactly the same as the previous equation, yes? When you've got an air column, or you have one end that's open and one end that's closed, would mean you have a node on the closed end and an antinode on the open end.
What would that look like?
I'll show you if I can get that YouTube video. I don't have good animations to be able to show you this real well. Okay? When you have a node and an antinode, basically what happens is you skip every other harmonic because you don't have both open or both closed. If you have one open and one closed, what ends up happening is it's only every other harmonic. So you will never see the second harmonic, you'll never see the fourth harmonic, you'll never see the sixth harmonic, and so forth. Okay, so this is just a modified equation to be able to solve that. No, it would still be, you could still use the same equation. Like you're saying, if it was open and closed versus closed and open, that's still going to be the same. Okay, I want to get to, so this is just showing you what it would look like. Here you have open on both ends. Actually, this is not a good example. I'd rather just get to the YouTube video. This just looks way more confusing than it has to be. Okay, I do want to quickly get to a problem to show you something.
It's like a bang bullet.
Oh, I didn't start the stupid, or did I?
I don't know. You started to get it.
Did I?
After you said you were gonna slap me.
No, I shut it off.
Shut it off.
Oh.
That's okay.
Where is it?
It's all
Anyways,
the
there it is.
wrong.
mean, no one's missing, so.
That's
true,
future
man.
generations.
Yes.
Okay.
Our mark isn't gonna be left on them for this class.
Okay. So here we are. We did, what are the first three harmonics of a 2.45 meter long pipe? So your L would be,
3.
2.4, oh wait,
I lied.
2.45.
okay? That is open at both ends. So if it's open at both ends, you have the full set of harmonics, which would mean F is N
B2L.
V over 2L, right?
Yeah.
Okay. N can be 1, 2, or 3. This is referring to the first harmonic. What do we call the first harmonic? It has a name.
The
Fundamental frequency. Okay?
If we said foundational, we'd be wrong. That'd be wrong.
Foundational frequency?
Yeah. Because they sound similar, and
Okay.
I feel like I'm gonna get confused.
Try not to.
Okay.
Then you don't have to worry about it.
I'll spend
Okay.
extra time.
What are the first three harmonics of the pipe when one end of the pipe is closed?
What? Doesn't that mean 1.5?
So then it wants both. So we're essentially doing it with it open and when it's closed. Okay, and I will show you a quick way to be able to do this. Okay, let's just find the fundamental frequency, which would be F1. Correct? N is 1, I can just ignore it.
Yeah,
Correct?
correct. V is 345 meters per second.
Oh yeah, there it is. Sorry. I was like,
Therefore,
speed.
you plug in chug. Wow. It's crazy.
Price.
Divided by 2L.
Okay, so when you do that, you will get your fundamental frequency to be 70.4 hertz.
Oh.
Now,
Did you just multiply
yes,
that? So then by 6 and then by 6.
yes, essentially, yeah. So your second frequency would be 2 times that. Your third frequency would be 3 times that.
Oh, great.
Now, we could go back and go back to that visual where it had 2L, L, 2/3 L. Yeah, we could do it that way, but this is way easier.
So is the N just the one times, remember?
Yes. Well, I mean, you could go all the way up to whatever.
But what is N?
Because it says it wants it for the first 3 harmonics. So that would be harmonic 1, harmonic 2, harmonic
So
3.
N represents
N1, yes. Yes, N represents your harmonic. Okay? Then it wants to say where it's open on one end, closed on the other. We have a different equation for that, right?
Yeah. But this first is still going to be the same.
Oh yeah, no.
No.
So multiplied by 4 instead.
Oh yeah, that's right.
It'll be half.
Okay? So when you find the first one, it's still going to be 1. Still got 345. 4L, so it should just be half, correct?
Yep.
Is that what you guys already said?
Yeah.
And then we multiply that by 3.
Okay, what is half of 70.4?
And we do 1.5.
Yes, because this is open on one and closed on the other end, you don't have the full harmonic series. Okay, and I know you don't understand why. I wouldn't get too caught up, that's a much higher level.
Advanced physics.
Much higher level. And so technically the second harmonic would actually be fundamental, or the frequency 3.
So it's
Yeah.
6.
105. Well,
Three,
yeah,
six,
yeah,
six.
6.
And then the fifth
It's 176.
What's the second one? What's the second?
The
second one is, so it's 135. So.
Why did the third?
It's 176.
Oh, the number? 106.
For the.
So this would be
Oh,
closed on one side, both open.
What do you do? Is that the top one?
That's what a string, like a guitar would be. Would be
That's the
closed.
top one?
Yeah, it would be this. So,
the top, that
both
one's-
open, both closed would be that. The only time you're gonna have a difference is when you have one open, one closed. Both open or both closed will both be this. Okay, and it should be in your notes.
And our answers are just those 3 answers for each.
For this
And
particular.
you only go 1 through 3.
It's,
Oh,
well, it
it's
asks
over
us
there.
for the 3, okay? I want to show you a YouTube video here, because it kind of puts it in perspective of what, with some visual effects, what it looks like. So,
Yeah.
if, I wish when I was homeschooled, Khan Academy was big.
Wait, what if it's closed on both ends?
The same as.
Same as open on both ends.
Oh yeah, I knew that.
What?
Should we ask Cole's name again?
Right.
So you came up with a theory.
I didn't say
Literally
one
was
word.
sitting up and about to fall over.
I didn't say one word the whole lesson.
No, I'm saying
Why do you make that noise? How come you get that loud sound? And it has to do with something called standing waves, or a very closely related idea is resonance.
Oops, I did turn
So
it
we're
on.
gonna talk about this. How do these work?
Please listen.
Let's go into here. What I've really got, I'm gonna model this. I'm gonna say that I've just got a soda bottle. I'm gonna model it like it's just a tube, a simple tube, and one end is closed. This is important. This end over here is closed. I tried to shade it in to show you that this end is blocked off. That's the bottom of the soda bottle. This is on its side. And this end over here is open. And so what happens, you've got this closed end, you've got this open end, you've got air in between. What's the air do? Well, when I blow over the top, the air starts to move around, but this air on the closed end, it's pretty much stuck. If it wants to oscillate back and forth. That's what these air molecules want to do. But every time it tries to oscillate, it just bumps into this closed end, loses its energy. And it try it again, bumps in, loses its energy, so it doesn't really go anywhere.
That's why you have a node
Whereas
at
on
the
this side,
closed
the
end,
side's
because it
open,
can't
shoot,
move, it
this air
just
can
sits there.
dance like crazy, oscillate back and forth. It wouldn't go that far, I'm exaggerating here so you can see it. But this end will oscillate much more than this other end. This closed end, the air just stays there. In the middle, it'll oscillate somewhat, somewhere in the middle. And so if you wanted to see this, I made a little animation so you can see this happen. Here's what it would look like. You see that the closed end, the air's not doing anything. At the open end,
That's what the air would look
the
like.
air can oscillate wildly, and in the middle, it's varying amount. They get smaller and smaller as you get toward that
I want
closed
to
end.
stop this quickly,
Oh.
because notice it's moving and then going back to equilibrium. Or actually, it moves
Over.
and goes back into equilibrium, goes past equilibrium, goes back to equilibrium, goes past equilibrium. And that's why you get the antinodes that are max above and max below.
So, is this,
Okay, so
I was saying, is this like almost the same wave? Or is this?
Yeah.
It is?
Well,
So then,
I mean-
is this saying like the amplitude is higher at certain parts and lower at other parts?
Inside an instrument, absolutely.
Alright.
So that's this bottle. That's how we're modeling this bottle here. So you can do this if you cut the bottom out. If you cut the bottom out of the bottle, you'd also be able to set up a standing wave. It would look like this. So let's say we've got an open end on both ends. So now we've got an open end on both ends. This side is open. This side here is open. This means the air now on this side isn't stuck anymore. This air can oscillate like crazy. This air over here can oscillate like crazy, and it turns out if you blew over a bottle that was cut open on both ends, or if you just had a PVC pipe and you blow it over the top, you'd get another resonance, you'd get another standing wave, and in the middle, this air molecule would just stay still. These would oscillate like crazy on the ends, and this is what
So now you got your node in the middle,
a little bit like
and your
this.
antinodes at the outside.
So both ends oscillating like crazy, and then right in the middle, air not really moving at all. So this is a standing wave. It's a standing wave. I actually don't like that name. I like the name dancing wave. I mean, the air is still moving. This air is moving back and forth. This air is not, but lots of the air is moving back
I
and
like
forth.
that
And they call it a
animated
standing
visual.
wave because no longer, remember with a wave you had this compressed region, and what it looked like the compressed region was moving down the line with some velocity. So this is a moving wave. But when you set up a standing wave, I'll show you again, this standing wave doesn't really this one here, say, it's not really, the compressed region doesn't look like it's moving down the line, everything just kind of bounces back and forth. So, how do we describe this mathematically? That's the hard part. This is the part that drives people crazy. What we could do, we could try to draw lines. Let's draw some lines that represent where all the air particles are in their equilibrium position. Equilibrium position is a fancy name for, this is if the air was,
You guys know what
this is our open tube, and this is what the air is at when you're just not messing with it. The air is just in this position, just hanging out. And I'm going to draw these lines here so that we know this is where they want to be, and when they get displaced from that position, we'll be able to tell how far they've been displaced. So if you did this, you took a PVC pipe, you blew over the top, this is what the air looks like before. Sometime afterward, it might look like this. Now the air is displaced, so check it out. This one got displaced all the way over to there. This one went to there. This one went to there. This one went just a smidgen over. This one didn't go anywhere. This one went to the right. And this one went to the right. This one went to the right. This one went way over to the right because it's at the open end. So you've got varying amounts of displacement at different points. So what we're going to do, we're going to graph this. I'm going to make a graph of what this thing is doing. So let's make an x-axis, a horizontal axis. This will represent where I am along the tube. And then we'll make a vertical axis. This will represent how much displacement there actually is. So this top end, so this will be displacement. The amount of displacement of the air molecule, and then this is just position along the tube. Where exactly am I along the tube? I'm just going to call it x. And so if we graph this, what are we going to get? Well, what we're going to get is, right here, this air molecule at this x position has displaced a lot to the left. And usually leftward's negative, so on this graph, I'm going to represent it down here somewhere. I'm going to just pick a point down here.
See how he's max displacement there? He's really far away from X.
I'm going to graph this. That's a lot of displacement. This one didn't displace at all. That was just right in the middle. So that's got to be on the axis because that represents zero displacement. This is zero displacement over here. And then over here, it displaced a lot to the right. So that would be a lot of displacement to the right. And in between, it's varying amounts, and it would look like this. You'd get a graph that looks something like that. And what is this? This is a standing wave. This is what we'd see, but it wouldn't stay like this. These particles would, this one in the middle that keeps on not doing anything, but this one over here would then move all the way this way and oscillate back and forth. And so what you would see this shape do, if you played this in time, this would start to move back to equilibrium, so this spot would start to move up to here. You'd get another point in time where it looked like this. Everything not nearly displaced as much as it was before. And then you wait a little longer, it goes flatline.
That's when everything's come back
to its equilibrium position. Then this one over here starts to move to the right, so now it's a little bit further to the right than its equilibrium
What are you trying to see?
And eventually it's flip-flops like this, and so you get a graph like that. So this is what happens. If you watch
This
this
would be
graph,
half a standing
this graph
wave,
would dance up and down.
or one standing wave, which would be half the
All the
wavelength.
way to the bottom, and it's good to know that does not represent an air molecule moving up and down. These air molecules do not move up and down.
Yes.
They move left and right. And this graph that we're drawing represents the amount they have displaced left or right. And so this graph, this peak, called the standing wave, because this peak does not, this looks like a peak, right, on the wave, on this graph right here, this peak does not move to the right. It dances up and down now. That's what this thing does. I wish we could have called them dancing waves, but they're called standing wave. These peaks move up and down, and the node, this guy just stays right here. If this was a regular traveling wave, you'd see this
Which
node
when they
move
had
to the
that
right.
moving,
You'd see this
when you
peak
had the
move to the
moving
right.
thing,
It doesn't do that.
the middle one didn't
We
move
call
at all.
this
It
a
just
standing
stayed
wave.
right there.
And
That's
I
where
already
your
said
node
at
is.
this point in the middle,
Because it never
given
gets,
the special
it never
name,
goes anywhere from
this point
displacement.
right
It stays
here is
at
called
equilibrium.
the node. This is a node, and these points at the end, this location here and this location here that oscillate wildly are called antinodes. So the antinodes are points where it oscillates wildly, and the nodes are points where it doesn't oscillate at all. This particle does not move, and this point on the graph just stays at zero. So the tricky part is, how do we represent this mathematically. This is how we represent it graphically. How do we represent this mathematically? Well, let me clean this up a little bit. The question is, how much of a wavelength is that? How much of a wavelength is this? Well,
What would you guys say?
one whole wavelength. I'm gonna draw a
Half a
whole
wavelength.
graph over here. One entire wavelength looks something like this. Here's a graph just to represent a wave versus x. An entire wavelength is when it gets all the way back to where it started. So from some point in the cycle, all the way back to that point in the cycle would be one wavelength. How much of a wavelength is this? Well, look, this is only, it starts at the bottom, and then it makes it to the top, but that's it. It stops there. So the question is, well, is that a whole wavelength? No, it's only half of a wavelength. So if we wanted to know how much of a wavelength is this in terms of the length of this tube, say this
So
tube
this
has
is
a
kind of what I was explaining
for this first
earlier,
one,
what he's about to
we
explain here
realize
is
that,
how
okay,
half a
that's half a
wavelength
wavelength,
is
so L,
gonna make it so
one
that
half of
it's
a wavelength
2L
is
as a
fitting
full
into
wavelength.
the length L. So this one half of a
That's your
wavelength
fundamental
equals a
frequency.
certain
Yep.
distance. The distance that one half of a wavelength equals.
Because this is the longest wavelength you could have, even though
One half.
it doesn't represent a full wavelength, but this,
What
you
that
can't get any
means
longer.
is lambda,
So it's not
not
like
2L.
the entire
So
left
this
side
is
is like
it, the
theoretically.
lambda of this wave
And then the right side would be.
is 2L, and we call that the fundamental frequency, so the fundamental.
Yeah, so all the, in theory, you can say where it's
This is the one that you're here. This down now, this is the
If
wavelength.
it's like a
If it's a top, there's,
oh,
so
sorry.
if this
I thought you were
is
saying-
theoretically all
Yeah.
the lines here.
This
And then
three
this
is
is
two, harmonics.
Who is that? That's great.
yes, they would have, is you have like this. That would have the wave, or probably right here. See, that would be much more. You have a bottle of and you close the lid. It's like the first one,
It's a pole.
Ooh, video camera.
It's a pole.
Pulling.
Well, you're saying that it's being open. So basically, people using it as.
Well, we need to test it.
Why would you blow? So it's creating half on those. So that's the way. Yeah, when it's like, they have that. With the molecule.
I was like, with the.
I put them on, I thought they were mine from mom.
I felt so bad because I have.
They can get out.
Before.
And then also, to the added 15, she said she just happened to see.
I
I think we do it today.
I still felt bad.
Okay, all right, I'll do that, yep.
Thanks.